Thank you, Tom. We are definitely going to take a change of pace because we're going to go ahead. Oh, let's see here. Okay, fine. We're going to go ahead and start looking at really a completely different side of the problem. In fact, Sunday we had a great presentation by Sam Baldwin in looking at what are the real limitations, what is the limits in terms of the maximum amount of different kinds of renewable technologies that could be implemented in this country. And what I'm going to do today is go back and say, let's look at one building and let's look and see what is the minimum amount of energy that we could use in that building without violating physical law while providing all of the services that we have in that building today. In the buildings area, there's a lot of talk about carbon neutral buildings, of course, where you would use all of your energy from renewable sources. At another level, there's a lot of talk about net zero energy buildings where the total energy generated from renewable sources on site over the course of a year is equal to the total energy consumed in that building over the course of a year. And so if you're looking at that, when you start looking at these net zero buildings, for example, one of the problems people run into today is if you don't have enough room to put photovoltaics on the roof to handle the entire consumption of the building. Obviously, one way that they deal with the problem is to try and squeeze that down by making the building more efficient. And if we look at that, why certainly that will give us more flexibility in the design and construction of the building. Certainly today, a lot of efficiency measures are lower in cost than adding more energy to the building. And at another level, one of the things that people talk about a lot in the buildings community is providing buildings that are 30 or 50% more efficient than the minimum code building. Yet, if I look at what has happened ever since I started thinking about these problems 35 years ago, people have always said that buildings can be about 50% more efficient than they are today. And yet today, why buildings are much more efficient than they were 35 years ago. And so I thought it would be interesting to sort of try and explore what we might call a Carnot limit for the efficiency of a particular building. Now, to do that, I said the easiest way to do it is simply to take the building that our lab operates in. We share it with the Texas Center for Applied Technology. We occupy about 2/3 of the building. It's a very simple building. It's just tilt-up concrete construction. It's a rented building. It's not an energy efficient building. In fact, we'll sort of see some of the characteristics here in a moment. It was a rented building that we didn't have the opportunity to determine what building we were going to rent. The university decided what building was going to be rented for us. So let's see. What this building is a building that I will call a minimally code compliant building. Because when I started to look at the specifications for the walls and the windows and so forth, I came to an interesting discovery. Not the only part of the building that actually met the prescriptive building code were the doors, and yet it passed the code check. So I thought, well, okay, somebody handed something to the building inspector or whatever. But then I had our folks take the code compliance software and run it on the building. And lo and behold, according to the code compliance software, it passed in spite of the fact that the envelope had 20% higher losses than the prescriptive code, minimum code building. So anyway, make of that what you will. The air conditioner is sort of a minimum, the lowest efficiency that passes that you can build today. The one thing I will say is they put a reasonably efficient lighting into the building, has electric heating and what have you. Okay. Now, if we look at the consumption of this building, measured consumption is about 350,000 kilowatt hours per year. That's 14 kilowatt hours per square foot per year, which is not bad. I mean, this is sort of a nominal $1.50 a square foot building, and a lot of buildings use more than that. The usage is roughly distributed as shown here between ventilation, cooling, lighting, etc. Okay, so in this building, what do we need? Well, just the same kind of things that most folks need. We want to have the building heated and cooled. We want to have some ventilation so that we have what we might call healthy air or acceptable air. Lighting we need. We have computers. We've got a lot of engineers. While it's the Energy Systems Lab, it's actually an office building because our experimental facilities are basically buildings, and then we have another facilities several miles away in an old fire station. We've got copiers. You know, we have water coolers that cool the water that we drink. There's a little bit of hot water used in the restrooms, etc. Okay. So I said, well, let's suppose that we're going to take the energy just as we're using it today. And while this building, unfortunately, doesn't maintain anything like 73 degrees, since we've got some offices that have hit 85 and 90 degrees on occasion because of the very poor system that the builder put in. We'll have ventilation that meets the ASHRAE standards, lighting that meets the lighting engineering standards, everybody have a computer, a couple monitors, a printer, and then we'll have a couple of copiers in the building. We'll assume that people are drinking more water than they probably drink. We'll assume people drink a quart of water per day from the coolers. That basically we end up heating enough food to amount to either a cup of coffee or you know, equivalent in microwaved food. We have some warm water in the restrooms, and the building is basically, people start showing up about 7:30 in the morning, and they're pretty much gone by that at night. So we'll assume it's occupied 12 hours a day, 5 days a week, which is reasonably close. Okay, so for all of these uses that we've talked about then, what is the minimum amount of energy for which we could provide these services without violating any physical law? Now, if we look at lighting, why, I said, okay, if you look at the lighting requirements that the illuminating engineers tell us we need, it's somewhere between 20 and 50-foot candles. For people my age, why it's probably closer to 50-foot candles, and for some of the younger ones here, it may be closer to 20-foot candles. But since we're talking about a building that will meet their needs, meet people's needs, we will assume that we've got control so that if somebody needs 20-foot candles, we'll have control that will do that, etc. How efficiently can we generate that? Well, people generally think of the visible spectrum of light from the sun as being, you know, pretty close to perfect light. And so we will simply assume that we are capable of converting electricity into light that meets that solar spectrum from 400 to 700 nanometers, corresponding to a 5800 Kelvin black body. And this basically says that we will have something like 250 lumens per watt. Now, we're going to control these lights so that they go off when somebody isn't in their office. They go down the hall for a meeting, or we have quite a few people who work off-site a significant part of their days. And so if we assume 6 hours per day actually in the office, that's probably a reasonable assumption. Then we have people that are gone like I am today. That basically ends up, we say, okay, let's assume an average of 35-foot candles, since we have people ranging from young to old in the building. And with these assumptions, that corresponds to something like 0.13 watts per square foot when it's occupied. And we assume a lower level when it's unoccupied, because there are a few people show up occasionally. So that says that we would need 1.7 kilowatts of lighting on average for this building if we have no day lighting. Just for comparison, a typical number for a building is 1 watt per square foot for lighting. So that would say 25 kilowatts for this building. So you can see we're way down here in terms of the actual lighting requirements that we need. Now, obviously some buildings can use a lot of day lighting. And I've seen some buildings where they get 75% of their lighting from day lighting or more. I said, for our purposes today, let's just simply assume that we have a building where we build it and are capable of getting 50% day lighting out of this building. Then with that, we will end up using 850 watts on average to light the building when it's occupied, and we'll use 240 watts when it's unoccupied. Computers are one where there's been work done that will end where one could compute a limit, but as we've had allusions to iPhones before, and certainly there's no question that, in my mind, that if my iPhone were operating using its full computational capacity 6 hours per day, it would do more than the computing that I'm actually doing. And I think that would be true for virtually anyone in our lab. And so that turns out to tell us that we would, if we were able to do our computing that efficiently, we would then be using, and of course my iPhone has a small screen on it. We're not talking about the screens here, I'm just saying the computing. We could do all the computing in the lab for 147 watts average. Monitors, again, I don't know what the actual limit may be, but if we assume that we have a couple of monitors per person and then we look at them and we say, okay, we just look at the light emitted from the monitor and assume that we can generate that at a physical limit, that tells us that we will end up with something like 200 watts average for the monitors in the building for 128 people. Printers are one that, again, I wasn't able to come up with a hard physical limit, so I conducted, this is the only experiment involved in this particular presentation. I got out an old inkjet printer and I put a meter on it and I said, okay, let's print a page. And it came out to take about 0.07 watt hours to print one page with this inkjet printer. And so I said, okay, looking at paper consumption in the lab and so forth, we have about 2,000 sheets of paper per person per year that seem to be printed. And so if we do that, why, using this rate at printing, it would say that we need an average of 7 watts to power printers in the lab, assuming, of course, that we are able to have no standby losses and so forth. And since we're using a model where we say we're looking for a physical limit, we're in good shape then. Okay, copiers. This is one of the harder numbers, if you will, because the copiers actually monitor how much usage they get, and that's where the 2,000 page or copies per person comes out. And so we used the same number. We said, we'll assume that we can make a copier that's as efficient as the printer that we were using, so that takes another 7 watts to handle the copiers. The drinking water, now we go back to sort of more familiar territory because people talk about Carnot refrigerators all the time. Presumably most of us had a thermodynamics class where we had to look at a Carnot refrigerator for at least once. For many of you, why, you probably forgot it as soon as possible, but anyway. If we use a Carnot refrigerator to cool 1 quart of water per person per day from nominal 70 degrees to about 50 degrees, well, it turns out that that will require an average of 4.3 watts when the building is occupied. Then next we look at this heating and we do the same thing. Now, of course, heating water or food from room temperature up to nominal boiling, we have a significantly larger temperature difference, and so our Carnot machine does not operate as efficiently. And so now we go from 4 watts to 53 watts to actually provide this input for the operation of the lab. The drinking water, oops, I went backwards, sorry about that. Hit the wrong button here. Water for the restrooms, we aren't heating it up as hot, and so it's a little bit more efficient, but that we're using a little bit more water, and so that turns out to be another 31 watts. Okay, now let's look at heating and cooling, since I recognize that most of you don't worry about heating and cooling computations and the usage in buildings. Well, here are the basic components that go into determining the heating and the cooling of the building. Basically, the electricity that's used for lighting and other uses inside a building is all converted to heat. And so if in the summertime at least, why, we have to remove all of that using the air conditioning. The occupants, I mean, each one of us is Well, the way you're sitting out there right now, each one of you probably corresponds to about a 100-watt light bulb. If you're moving around a little bit more, I'm probably 150, 200-watt light bulb right now because I'm moving around a little bit. And of course, if you get working out real hard, why, you can become a few 100-watt light bulb. Then we have solar heat that comes into the building through the windows. We've got to remove that, at least in the summertime. Then we have power for ventilation. If you recall the numbers we had earlier, something like a quarter of the energy in the building today is used for powering the ventilation fans. And then the one that people always think about, they tend to forget most of these and think about how much insulation we have in the walls. And for most large buildings, why, that's almost a negligible factor in the performance of the building. But we're going to look at each of those then and what the ideal performance could be for the building we've got. Well, all of the uses that we've looked at so far totaled up to just under 1,300 watts when the building is occupied. As we mentioned a little bit ago, 25 kilowatts would basically correspond to the kind of lighting load we would have in a building like that today. Then if we look at the gains from the people in the building, and we assume that it's just sort of moderately active office work, and use the numbers, why, it turns out that we're talking about people that are about 130-watt light bulbs on average. And so that turns out to be something like 11 kilowatts compared to the 1.3 kilowatts from all the electric uses in our building. Rather different from the way things are today, but it says that the people would then become one of the biggest heating loads the cooling loads in this building. If we look at the solar gains through the windows, I'm basically going to assume that since we're talking about physical limits, that we're smart enough to have windows that can shut on and off and just let in just enough light to do the daylighting that we're going to do in the building. And so if we do that, why, then we say, okay, we have about 850 watts of solar gain on average when the building is occupied. We look at the ventilation limit. We need a couple thousand CFM of ventilation air. And of course, if we have a perfect enthalpy recovery device, why, then we're not going to have to put any conditioning energy into that. And incidentally, it's interesting that there are materials being looked at right now that will let us ultimately, I believe, come very close to this, probably get at least an 80 or 90% effective enthalpy recovery device with very low fan power losses. We're going to assume that the building doesn't leak, and so we have the exhaust air equal to the inlet air, so this perfect enthalpy recovery device can operate, and we'll assume a very low level of fan power. I mean, in theory, we probably don't need any, but we threw in 5 watts for fan power. Now, the window, wall, roof. How many of you remember adiabatic walls in thermodynamics? No? Okay. Not very many. People shut that out as soon as you can, but we always are assuming adiabatic walls and devices and what have you in thermodynamics, so that's what I'm going to assume here since we're looking at physical limits. It's interesting, the first time I gave this talk to some of the folks in lab, why, one of the engineers, and he was sure that this had just totally blown everything out of the water. Well, as I said, when you look at it, actually, with what we can do today, we could still come very close to the assumptions we've made here if we just used 5 or 6 inches of foam, and it would make a relatively small difference in the final answer we get here. Okay, now, how are we going to end up meeting the heating and cooling loads in the building? Well, first of all, we're going to do something that we do today. When it's cold outside, we bring in cold outside air to provide the cooling needs in the building. And we're going to assume that we have perfect heat exchangers to do that. And so we're going to use what we'll call free cooling whenever the ambient conditions permit that. We'll use a Carnot efficiency, chiller otherwise, and then we'll use a Carnot efficiency heat pump to provide the heating needs of the building. Okay, we'll assume Houston, Texas weather. Total cooling is 40,000 kilowatt hours thermal. Now remember, I'm basically using a thermal measure equivalent to the electricity since we've been using electric inputs into it. It turns out that we can meet 60% of that with free cooling, even in the Houston climate, if we have this perfect enthalpy recovery device. The chiller then is going to have to meet 15,000 kilowatt hours thermal, but since it's a Carnot device in Houston, it will have an average COP of 62, so it'll take 250 kilowatt hours to meet all of the cooling needs of the building on an annual basis. Now, heating load, it turns out, since we have this envelope that's perfect, it never gets cold enough. I mean, regardless of how cold it gets outside, we're not going to need any heating in the building. And so our heating electricity is zero. Now, let's look at how this building will compare with today's buildings. If we look at the average office building in the US today, it uses 82,000 BTUs per square foot per year. The ESL building uses about 50,000 BTUs per square foot per year. So even though it's minimally code compliant, it's down at about 60% of the US average. This Carnot limit building uses 730 watts per square foot per year, less than 1% of the average in US office buildings today. Now, if we look at the implications of that, I mean, what does that say? Geez. That says that if we could build buildings like that, you could provide the same square footage of office space for every person in the world on a per capita basis as we have in the US today, and use 25% of the energy that we're using for office buildings in the US today. I mean, it has incredible implications for, where we could go. Now, could we get there? Of course not. And let's just look at, the building here, this building that I've shown at the bottom of the building is a building that has just been completed in Seattle. It was designed to be the most efficient office building in the US, and it was planned for 16,000 BTU per square foot per day. It also, if you notice, it has this hat on it. It's a zero energy building, and so they put enough photovoltaic arrays on the building that in Seattle it is expected to generate as much energy as it consumes. If we then go on and say, well, what about peak demand? Because peak demand is the other thing we've been talking about throughout this session. Well, our ESL building, the measured peak demand in the summer is 138 kilowatts. In the winter, it's 178 kilowatts because it's resistance heated, and so the peak is a bit higher there. And so what I did here, let's see, there must be a button on here that I can, is there? Well, anyway, at that top picture, if you see what looks like photovoltaic arrays, that's some digital imaging put on top of our building, a Google picture of the building, and it extends a bit beyond the boundaries of the building because we would need about 20 or 30% more photovoltaic array area than the area of the top of the building is today to meet that demand. To meet that peak demand with photovoltaics. If we look at that array down in the bottom, on the other hand, our Carnot limit building would have a peak demand in the summer of a little over 2 kilowatts. And so that would take about a photovoltaic array about the size of the one on this little trailer that used to sit parked outside the building. And so we can see it's a tremendous difference in the amount of photovoltaics that we would need for this Carnot limit building vis-a-vis what the building would be today. And this, I'm not saying, is the zero energy building. This is simply to meet peak demand. Now, if we go a bit further, I like to say, okay, how close do you think we could get to that? One of the things I like to do is go back and look and say, okay, when I was an undergraduate or in graduate school, the state-of-the-art computer was the IBM 7094. It occupied, not a room as big as this room, but it was a room-sized computer. And in the 1960s, it cost several $1 million. And yet it only had a tiny fraction of the capability of the iPhone that we carry around with us today. That certainly gives us one measure of what we can do when we apply ourselves to a problem. I would say that incremental improvements are very important. We need to be working very hard to improve the efficiencies of devices, but what this really says to me is that there's room for spectacular progress in energy efficiency. And I think we really need to pursue some kind of disruptive change like this guy here with his rocket pack on him might be looking at. For example, I mean, we're looking at and we're building a prototype for an air conditioner today that approaches things from a completely different perspective. And if you look at the efficiency limits for this system, it will have a limit that is 1/3 the energy of a Carnot device operating between the traditional temperatures that we're. And I think this is the kind of change that we need to be looking at to see how close we can get to the kind of performance that we see as a so-called Carnot limit for the building. Thank you.
Well, thanks, David. I think we all need to have our stretch goals sometimes, and I think he laid them out for us for those who get involved in the building sector. So we have a couple questions time now. Well, I'll ask one right there. Just, I mean, how practicality in the next, say, 10 or 20 years, how close could we actually get to this?
Well, I don't know how close we will get to it. My best estimate is that if we were to build sort of the best building we could build in the next 10 years or so, I think we could probably get within about a factor of 4 of this. Would that be a cost optimum building? Probably, of course not at that point. Will it ever be? Probably not, because as we've seen, I mean, the costs of other energy sources, renewables, et cetera, are coming down, and so somewhere in between we will have the optimum. But for me, it's exciting to expand, shall we say, to look at what the complete range of space in which we can look for an optimum solution is. And certainly, you know, as well, it was just mentioned in the last talk about the amount of materials that we may need for certain things if we are to go to using a particular system at a storage system at a grid scale, what have you. Things that we can do to provide the same services more efficiently are just fundamental good engineering in the first place, and I think they'll be good for the planet as well.
I believe we have a question right there.
Yeah, very good talk, Jeff Rinkemeyer. Just to put it in perspective, what percentage of our nation's energy is in buildings?
Ballpark it at 40%. So it's, you know, it's not the whole picture. And this is one building. It's not, you know, that's not saying that the entire building sector would be this low, because certainly as we've seen, I mean, if you go to say the food sale part of things, the fast food industry, they're not going to be able to achieve this much in the way of improvements because their delta T's are significantly higher and what have you. But I think it still, it gives us a benchmark, and I think it'd be very interesting to see the same kind of thing applied across, you know, all sectors to see what kind of a limit we might be looking at there.
Any other questions there? And I think that maybe elaborate on that 40%, and it's roughly half commercial, residential, and the residential and commercial markets are very different in terms of what you could do there.
Yeah, definitely.
All right.
Thank you.
Thank you, Dave.